Hi, this is Jack Jackson, and this is part 14 of our series of lectures on discrete probability. This lecture is on the binomial distribution. This is a pretty important distribution because it shows up in a lot of ways. So, in a binomial distribution, we're going to perform a fixed number of independent Bernoulli trials and let x be the number of successes that we observe. The probability of success in each trial has to be the same, which we're going to call p. So let's review what we mean by this. Bernoulli trial, remember, we divide the sample space into two parts. One part we call a success and the other is called a failure. The probability that we get a success is going to be p, and of course then the probability of a failure is 1 minus p, which we're going to also call q. Now, that's one Bernoulli trial. What we're going to do is we're going to do a Bernoulli trial several times. These are going to be independent trials, so the probability is p every time. So we're going to do the same thing over and over again. And the probability is p each time. But we're going to do this a fixed number of times. So we know ahead of time how many times we're going to do this experiment or do the trial. And that's going to be n. And then x is going to count the number of successes. And that's going to be 1. After we do all of those n Bernoulli trials, that's going to be 1 experiment for this binomial distribution. So let's look at an example. Suppose we roll a fair die and let a success be getting either a 5 or a 6. We're going to repeat this 4 times and count the number of successes. So think about what we're doing here. We're taking a die, we're rolling it, and we're going to see if it's a success. If it's a 5 or 6, it'll be a success. If so, we kind of record that. Roll it again, record, again, and again. So we're going to roll 4 times, count the number of successes. That is doing the experiment 1 time, and that gives us an x value. That counts the number of successes. Another way, maybe a more efficient way to do it, if we get our hands on 4 dice, is to roll all 4 dice at once and just count how many successes we get out of the 4 dice total. That's going to be the x value, and that rolling all 4 dice is going to be 1 trial of the experiment. So we're going to do the experiment 1 time by rolling 4 dice. Alright, so this is a binomial distribution. So I got 2 real basic questions here. What is n, and what are the possible values of the random variable x? Go ahead and figure that out. Press pause now. Okay, well we come back, and hopefully you realize that n is just 4. That's just how many times we do the Bernoulli trial. It's how many times we roll the single dice in succession, or, better yet, how many dice that we're rolling at once. Notice it's kind of like we're taking a sample of 4 Bernoulli trials, a sample of 4 rolls, and n is our sample size. In fact, that's why we use the same letter n that we did for a sample size when we were doing descriptive probability, or descriptive statistics rather. Now, in this case, what is x? Well, x is the number of successes, and so hopefully you can see that that could be either 0, 1, 2, 3, or 4. Notice you can get 0 because you might not get a success at all. But you can't get a number between these. You can't get a number less than 0 or a number of successes bigger than 4. So it has to be specifically one of these 5 numbers. Now it's important that we actually do this experiment. So I want you to actually complete this experiment by doing it yourself. So actually what I'd like you to do is actually go and find 4 dice and actually roll all 4 of them and record the x value. How many successes you got. How many 5s and 6s in total that you got. Record that. That's 1 x value. You've done the experiment 1 time. Do the experiment 20 times, which means you're going to roll the 4 dice 20 times, 20 sets of 4 rolls. Recording x each time, and then we're going to make a table. Now, if you don't have 4 dice, just get 1 die, roll it 4 times, find the number of successes in the 4 rolls, and then again you've done 1 x value. Repeat that 20 times. So make a table of the frequencies. You already know the x's are 0, 1, 2, 3, 4. We want the frequencies of each of those. And then divide by 20, divide by the total number, and that's going to give you the relative frequency. You might do that in a fraction, but then you also maybe do it in a percent form. And these are called the empirical probabilities. Now remember, empirical probabilities really are not probabilities. What they are experimental results that are relative frequencies. But of course what they are is our estimates or approximations of the actual real probabilities, which are theoretical in nature. And so we want to graph this as well. So we take our relative frequencies and graph them, and now we have a relative frequency histogram or bar graph. That relative frequency histogram is an estimation of, or approximation of, the graph of the PDF of the actual distribution, which is the actual probabilities. And, likewise, the table of relative frequencies, empirical probabilities, are an estimation of the table of the actual PDF. So, again, I think it's important you actually do this. If you can't get your hand on a die at all, then just use the die simulator in your calculator. But please go ahead and do this. You may want to actually just stop this video, do that, and come back, or at least press pause now. Well, now you're back. Hopefully you've done this experiment, and you got some feel for what's happening with the binomial distribution. Let's continue on. Now what we want to do is go in and actually figure the actual real probabilities, their theoretical probabilities, and to do this we want to make actually a probability tree and a table of our PDF. So we want to make a table. Of course, we know the x values on the PDF are 0, 1, 2, 3, 4, and we want to figure out the theoretical probability for each one of those things and make it into a table. To do that, we're going to first make a tree. So I want you to do actually two things here. Make a tree and a table for this PDF, for this binomial probability distribution example. This may take a minute. Go ahead and do that now. Press pause. Well, now you're back. Hopefully, at this point, you came up with a table and, well, a tree first, and use the tree to get you a table. See if yours looked anything like mine. Here's the table and coming from the tree for this probability distribution. So notice that, as in any binomial distribution, we start with our root vertex, and we only have two branches coming out of that, two edges coming out. Either one's leading to a success, and the other leads to a failure. Of course, a failure is just not a success, right? It's the complementary event. And the probability of success is labeled there with a p, and p is 1/3 or 0.3 repeating. So that makes q, the probability of a failure, 1 minus that, so the probability of failure is 2/3 or 0.6 repeating. And the table, or the tree, goes 4 deep. So the first column there of S and F is what happens on the first die. The second one is what happens on die number 2, the third column for die number 3, and the fourth column, die number 4, or the first, second, third, and fourth row of a single die if you did it that way. So, this tree keeps up with all of the outcomes. Now, I did a little color coding here to help us make this tree more readable. So, all the successes are vertices that the vertice and the label is in red. So the vertex and the label on the vertex is red if it's a success. And it's purple for the vertex and the label on it with an F, of course, if it's a failure. Now the probability of success each time is P. So coming into a success from the left into the success has to be a probability P, and so I labeled all those in green with a label with a P, which of course is 1/3 in this case, and then also I labeled that edge green, or made that edge green to make it a little bit easier to read. And similarly, if we're coming into a failure, that happens with probability Q, and those are black with the label of Q in black, and it also the edge is black. So those all represent a probability of 2/3 of Q. Now, let's see what else. P plus Q, of course, has to add up to be 1. And one of the things we want to do is figure out the probability on the whole path through the tree. Now, remember that the path through the tree, what we're doing is we're multiplying the probabilities, because after that first probability, every probability from there on is actually a conditional probability, and we're using our conditional probability multiplication rule to multiply these things out. Now, of course, in this case, all the probabilities are independent And so the probability of S is P every single time. And that's important for it to be a binomial distribution. That's one of our conditions. And that's, of course, the case in this case. It doesn't matter what we rolled on the first die. That has no effect on the second one. It's still a probability of 1/3 of a success on each die. So, if we want to find the probability of the intersections, for example, the top path would be success, 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 success. That means we had all 4 successes in a row. So the probability of that it's a success on die 1, and a success on die 2, and a success on die 3, and a success on die 4, we're unioning those sets, those events. And so the probability that you get all 4 successes is we just multiply those probabilities out, just like we do with any probability tree. And so this turns out to be P times P times P times P, or P to the 4th power, which you can see I've got labeled up in pink over there. Now this is actually 1/3 to the 4th power, which is actually 1/81. That approximately works out to be about 0.01235. So we got some decimal approximations for some of this stuff worked out here. Now the next one goes success, 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 failure. Notice that's P times P times P times Q, which is 3 P's and a Q, or P cubed times Q. Now the next one is success, success, failure, success, P times P times Q times P, but it's still 3 successes and 1 failure. So it's still 3 P's and 1 Q. So that's P cubed times Q. Same as the one above it. The next one is 2 successes followed by 2 failures. That's 2 P's, 2 Q's multiplied together. So that's P times Q times Q, or P squared times Q squared. 2 successes. The next one is back to 3 successes, but the failure is now on the second one. So it's success, failure, success, success. That's another P cubed times Q. The next one is success, failure, success, failure. Again, this one has 2 successes and 2 failures, so it's 2 P's and 2 Q's multiplied together for P squared, Q squared. And so forth. You can work on down the tree. And the last one at the bottom is the only one that has no successes, and it's all failures, just like the one at the top was the only one that had all successes and no failures. The one at the bottom has no successes, it's all failures, so it's Q times Q times Q times Q, or Q to the 4th power. So we can make our probability table based on this information now. Now, of course, we know the x's already. We're 0, 1, 2, 3, 4. Now, 2 of the y's, the probabilities of the values of the PDF, are real easy for us to figure out, and that's the one at the top and the bottom. So on the top of our table is x equals 0. That is the probability that there are 0 successes. Well, 0 successes, the only way to get that is all failures, and the only one path leads to that. That's the one at the very bottom, failure, 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 failure. That's Q to the 4th is that probability, so that one's pretty easy. That turns out to be about 19.8%. The one at the bottom of our table where x is 4 is actually at the top of our tree. That's going to be another one that's real easy because there's only way to get 4 successes. They're all got to be successes, and that's got to go up that top path. And that turns out to have probability P to the 4th, about 1.2%. Now, however, look what happens when we want to get x equals 1. Now, x equals 1 means we have 1 success, which of course means we have 3 failures. So that means that path is going to have a probability P times Q times Q times Q. In other words, P times Q cubed. But the point is, though, this happens 4 different ways. Actually, you've got this 1 success, and that 1 success may happen on the first time, or it may happen on the second, or the third, or the 4th die. So there are 4 different places there that we get that. Now remember, these probabilities at the end of a table are probabilities of intersections. They're mutually exclusive events, so these probabilities can just be added up. So in other words, you can always add up these numbers at the ends of the probability tree. So all of the ones labeled with the brown P times Q cubed all have an x value of 1 success. And there are 4 of those to add up. So the answer is 4 times P times Q cubed, or about 39.5% that will get 1 success. That's actually the most likely outcome. If we look at the ones for 2 successes, which of course have also 2 failures, so it's p squared times q squared for each one, it turns out there are 6 of those arrangements. So there's 6 ways of arranging those 2 successes and 2 failures. So that's a total of 6 times p squared times q squared, which is about 29.6%. You can see all 6 of those labeled with black p squared q squared in the tree. And finally, the ones that have 3 successes, there are 4 ways of doing that. We'll have 3 successes and 1 failure, so it's p cubed times q, and there are 4 of them because there's 4 different places you can put the 1 remaining failure. So that is 4 times p cubed times q, and that's approximately 9.9%. Now I'm going to work out the exact values on the next page. Okay, on the next page we see this. The probability that x equals 0 is q to the 4th, which is 2/3 to the 4th. That's 16 over 81. In fact, all the denominators are going to be 81 for these. Think about it. They're all just some combinations of p's and q's multiplied together. In fact, there are going to be 4 of those p's and q's in some combination, but all the p's and q's are either 1/3 or 2/3. And you multiply fractions by multiplying all the numerators together to get the numerator and all the denominators together to get the denominator. And so all the denominators are 3, and there's 4 of them, so we're going to get 3 to the 4th is 81 for the denominator. It's just a question of what the numerator is. So in this case, it's 16 over 81. And so that's the exact value for probability of x equals 0. And that is about 19.8%, and you also see the decimal as far as my calculator will go. Now, the next one is 4 times p times q cubed, and you can see that works out to be, well, the 1/3 times 2/3 to the 3rd is 8 over 81, and so that 8 over 81 is the p times q cubed, and that's the value, the Brown value of about 9.9% that's going to be at the end of each one of these with the Brown label in the tree there on that page. But there we have 4 of those guys, so 4 times that 8 over 81, that turns out to be 32 over 81 for the exact value of the probability of 1, and that turns out to be 39.5% approximately. So again, that's our most likely outcome. Also, our next most likely outcome is that we'll have 2 successes. That's 6 times p squared times q squared for the probability. And so the p squared times q squared is 4 over 81. That's the probability at the end of each of those pass through the tree where we had 2 successes. And there's 6 of those pass. So 6 times that is 24 over 81. And that one we can reduce to be 8 over 27 if we want. That's 0.296 with the 296 repeating, or approximately 29.6%. The next one, the probability that x is 3, is 4p cubed q, which is 4 times 1/3 cubed times 2/3. And again, we get an 81 for the denominator and just 2 for the numerator. So 2 over 81 is the probability that we get a particular path that has 3 successes and 1 failure. But there are 4 such paths for a total of 8 over 81. And that's about 9.9%. And finally, if we have 4 successes, okay, we get 1/3 of the 4th, or 1 over 81, or about 1.2%. And there's a little dead space in this graph down here, but you can see these 5 bars, one above 0, 1, 2, 3, and 4. And of course, they have the heights given above, 19.8% here. Well, exactly 16 over 81, 32 over 81, 24 over 81, 8 over 81, and then 1 over 81. And so you can see the graph of the PDF and the table for the PDF. And you've seen how we figure it out. So let's see if we can come up with a formula based on this. Well, notice each time, this part was pretty easy. Each path through the tree where x equals, let's say the number of x equals k is the number of successes. Then we're going to have k p's, and we're going to have n minus k q's multiplied together. So we know we've got this p to the k, q to the n minus k. The tricky part is that coefficient, because there was a number in front that counted how many multiple times that particular one, how many different paths that came with the same x value. How many are there going to be? Think about that a little bit. If you've got k successes and you've got n trials, how many different paths will lead to that? Go ahead and press pause and think about that a minute. Well, what we're needing to do is to count the number of ways of distributing the k successes among the n edges along that path. We have n edges, and we're going to choose k of those. Does it matter which, if we have two of them already labeled as p's, does it matter if we switch them? No. The order doesn't matter. So we're arranging things, choosing k of those things from a group of n, and the order doesn't matter. This sounds like something we learned how to do earlier. What is it? Did you come up with a combination or binomial coefficient? This is called a binomial probability. This is a binomial coefficient. This also has something to do with a binomial expansion. And this is n choose k ways of doing this. So that's the coefficient. So here's our probability density function. The probability that x equals k is n choose k times the p to the k times q to the n minus k. Or we might just call it p of x and replace the k's by x's. Alright, let's put this to work and see if we can try another example. Suppose you're taking a test that has 20 questions and each question is multiple choice. And each one has 5 possible choices. Now, let's suppose, I hope this never happens to any of you guys, but suppose that you're going in, you know absolutely nothing about the subject, and you're just completely randomly guessing. What's the probability that you will get specifically question 4 right? What's the probability question number 4 will be answered correctly if you just randomly guess? Well, you've got 5 choices, and only one of them is correct, so the probability you'll get that one correct is 1/5. In fact, if you take any one particular question, you're going to get 1/5 as a probability. So can you see that the number that you get correct is a binomial distribution? You've got n is 20 and p is 1/5. Because they're independent. If you're totally just randomly guessing, each question is independent of the one before, and each one you have a probability of 1/5. Now here's something I want you to think about. On average, how many would you expect to answer correctly out of these 20 questions? If we did this and we put, we gave 100 chimpanzees a way to guess the answers to a ProbStat question, multiple choice test, and had them choose, and they were randomly guessing, and we averaged out their scores, what would we expect the average to come out to be about? In terms, not the percentage, but the actual number of questions. So think about it. If the probability of a question getting it right is 1/5, we would expect to get about 1/5 on every question. 1/5 of the questions, which would be 1/5 times 20, which is 4. And so this shows us how, in general, we can find the mean of a binomial distribution. It's n times p. I did p times n here, but same thing. N times p, or p times n, is the mean of a binomial distribution. So here's a summary of what we learned so far, plus one new piece of information. In a binomial distribution, we perform a fixed number of independent Bernoulli trials, we'll call that n, and let x count the number of successes. The probability of success on each trial is the same, we'll call that p, and the probability of a failure on each trial is, we'll call it q, but that's just 1 minus p. The PDF formula is p of x equals k, the probability of x equals k, is n choose k times p to the k times q to the n minus k. The mean is just n times p, and we didn't prove this one because it's a little bit harder to prove, but I'm going to go ahead and tell you that the variance is n times p times q. That's the variance here, and of course the standard deviation would then be the square root of npq. Alright, let's try another example. Suppose we know that 5% of the removable holes manufactured by the Acme company are defective. Furthermore, suppose that Wile E. Coyote is buying a lot of 35 of them. So he's going to go out here and try to set some traps for the Roadrunner. Meep. So he's bought a big box of 35 of these guys, but we know that 5% of them are not going to work. Okay? So what's the probability that the first one he pulls out of the box is going to be defective? Well, any particular one that he pulls out of the box, the probability is P, which is 5% or 0.05. What's the probability of getting exactly 15 of them defective? Exactly 15 are defective. What's the probability? Well, this is a binomial distribution. We've got 35 of them we're choosing from. That's n. The probability of a success, which is a bad hole, is 5% or 0.05 for each one. And we're trying to find the probability that x equals 15. So that's exactly the probability that x equals k in general is going to be n choose k times p to the k times q to the n minus k. We put in what we know, that there are 35 holes in the group that we're looking at, our sample of 35. So it's 35 choose k. Probability of success, which is a bad hole, of course, is 0.05 to the k. And it's 0.95 is q to the power of 35 minus k. And specifically, we're interested in the probability that x equals 15. So that's 35 choose 15 times 0.05 to the 35 times 0.95 to the 35 minus 15. We can do 35 minus 15 in our head. That's just 20. And here I did that on the calculator. Remember, we got the NCR thing on a calculator to help us out. So we can do 35 NCR. Now remember, NCR is math, left arrow to probability, and it's going to be one of those first three there. Pick the right one, and then push 15 times 0.05 to the 15th times 0.95 to the 20th. And we get 3.553289949. That e negative 11 means times 10 to the negative 11th. Don't ever write it that way. Write it as times 10 to the negative 11th, which is really 10 zeros and then the 355, etc. So practically 0. It's not actually 0, but it's really close. It's highly unlikely he's going to get, very, very highly unlikely, he's going to get exactly 15 bad holes. Now, it turns out that we can compute this on the calculator. It has a shortcut. This is so cool. So, the probability that x equals k, again, we can see it up there, but we can get this on our calculator like this. And here you can see the keystrokes that you want to actually push. So you do second variables, which is, notice above the variables key, it's printed distribution, or DISTR, for distribution. So second vars will give you distribution. You'll get that screen there on the left. Well, not quite yet. Then you up arrow about, looks like about 6 times to get to A there, and then you'll be at the screen you see on the left, and hit enter. And you're choosing Binomial PDF. That's the binomial probability density function. Now, it's also A, so if you already know it's A, if you've do a bunch of these, you'll know it's A, and you avoid hitting all those arrow keys by doing second variables, and then do alpha A, and that'll give it right to you. And that, either way, you get on the screen after that first line of keystrokes or second variables alpha A, you'll be to the point on the home screen where you have Binomial PDF open parentheses. Now you type in the n value next, which is 35, comma. Now you type in the p value, 0.05, comma. And now you type in the k or x value, 15, close parentheses, enter, and notice this gives you exactly the same amount that we figured out before. Isn't that slick? That is so cool that we have this thing built in, and it saves us a whole lot of hassle. You just got to remember the right order to put things in. So it's binomial PDF, it's NPK, that's the order. The N is the number, the sample size that we're choosing, how many Bernoulli trials we have, the sample size. P is the probability of success for each of the element of the sample, and for each Bernoulli trial, and K is the number of successes that we're trying to find the probability of. So, Very cool. Now let me show you even more cool thing. Do the same thing. Get the binomial PDF. Again, you could do that. Well, the quickest way would be second and the variables button to give you distribution, and then alpha A will go directly to it, and that will give you the binomial PDF, open parentheses. Now this time put in the N and the P, but leave the K out, or leave the X or K, whatever you want to call it. Leave that out. So you got binomial PDF of 35, comma 0.05 close parentheses. So that's NP, N comma P in the parentheses. And look, you get a list. Now at this point, if you actually had your calculator out, you could scroll to the left or right on this list. Now I'm going to do one more step and say store that in L1. The store key is the STO with the arrow key down in the lower left. It's on the left edge down toward the bottom. And L1 is second one. And now notice that this stores the actual values of the PDF in list 1. So if you do stat edit, you'll get the screen in the lower right hand corner here, and you see there that that first number 0.16608 is the probability that x equals 1. I'm sorry, let's see, this is x equals 0, starts at 0 for x. No successes. And then the next one, 0.3059, etc., is the probability that x is 1, and then the next one for x is 2. So if you look at this one, the probability that there's exactly one defective hole is about 16.6%. The probability that there's exactly 2 is 30.6%. Probability that exactly 3 is 27.4%. Probability 4 is 15.8%. And then it starts going down pretty fast from there. But you get these probabilities. You can scroll down this list now to see them. So that's binomial PDF of N comma P, and then you want to maybe store it in L1, and then you look at L1, you can see the entire list. Alright, here we go. Suppose that 5% of the removable holes manufactured by Acme are defective. Furthermore, suppose Wile E. Coyote's buying a lot of 35 of them. So same thing against this. What if we want to know that no more than, actually I want to change that from 15 to 6. So no more than 6 of them are defective. Go ahead and figure that out. No more than 6 of them are defective. Press pause now. Now let's think about this a minute. When you say no more than 6, what you're doing is you can't get bigger than 6, but it could be 6 or less. So we're doing the probability that x is less than or equal to 6. Now one way you can do this is to do it the way we just did it, either without the CDF or with the CDF thing. Figure it out for 0, 1, 2, 3, 4, 5, and 6, and then add all those up. Or, guess what? That's just the binomial CDF, cumulative density function, evaluated at this particular one. I see another typo. This should be binomial CDF of 35, comma 0.05, comma 6, but at least I did it right in the calculator, so the answer is correct. And so this is this you can do. It's built in your calculator too. It's right next to the binomial CDF. So again, you do second distribution, and then I think it's B this time, is binomial. That should say CDF. This is incorrect. Let's see if I can. Let's see if I can just continue recording and get the correct answer here. Okay, and you can just watch me fix this. Alright, so this should say 35, and we need the CDF. And so that number may be wrong too. So let's go back here and work this out, and you can actually see me do it. So it's binomial CDF, so second distribution, and we can go up arrow if we want, and it should be the B, should be the CDF. There we go. Binomial CDF, and we have 35 we're choosing from, and the probability of a success is 0.05 each time, and then the probability, or then the number that we're trying to go up to is 6. This is the probability that we have 6 or less, and this is what we want. Yeah, it's very high. Okay, and so we have that right there. Let me go ahead and do one little thing here and put a border around that. Okay, and so there's the calculator, and now I need to go back to this and change that to match the correct answer. It's a very high probability here. 0.99847843331, approximately 99.8%. Okay, so let's go back to our slideshow and keep recording here. So notice in the previous slide, I'll fix that in a little bit, back here, what we're doing is we're adding up these 1, 2, 3, 4, 5, 6, 7. Actually, all the numbers we see here we're adding up because these are the probability that x equals 0 defective, 1 defective, 2, 3, 4, 5, and 6 defective. And so that adds up to be very high, nearly the whole thing, about 99.8%. So if he was to put a trap for the Roadrunner and put 6 of these in a row, there's a real good chance that this would work. But of course, this is Wile E. Coyote, so it never works for him. Alright, let's move on. What's the probability that there are at least 5 defective? At least 5. Press pause and figure that out. Now, let's think about this a minute. The probability that at least 5, that's the probability that x is greater than or equal to 5. Well, the CDF figures out the probabilities less than or equal to this. So what we want to do is the probability that x is less than or greater than or equal to 5 is 1 minus the probability that x is less than 5. But remember, you can't get anything between 4 and 5 on this distribution. Maybe you can in other distributions, but not this one. And so we really only need to go up to 4. So that turns out to be 1 minus the probability that x is less than or equal to 4. Well, that's 1 minus the sum of the PDF from 0 to 4, okay, which I've got all that written out here. But of course, in our shortcut, we can do this pretty easily. This is 1 minus the binomial CDF. That should say, I did it right over here on the side. This should say 35, 0.054. I'll fix these little details later for the other, for the standalone printouts. But here we see it's correct over here, so our answer is correct. That's 1 minus binomial CDF of 35, 0.05 and 4. Moving right along here. I wanted to compare and contrast the geometric and the binomial distributions. Both of them are very similar because they're both based on a certain number of independent trials. But they are Bernoulli trials, and the probability of success is the same each time. So that part's the same. But here's where they're different. A geometric distribution, which we covered in our last lecture, we do not know how many trials we're going to have. And x counts the unknown number of independent Bernoulli trials until the first success. We know there's one success. Of course, you'll have x minus 1 failures. What we don't know is how many trials it's going to take us to get that success. That's x. Contrast that with a binomial distribution. In this distribution, we have a known number of independent Bernoulli trials. That's n. What we don't know is how many successes, and that is x. So notice there's a compare and contrast here a little bit. Okay, nearing the end of this lecture, let's try another example. One more before we finish up here. Suppose we have an urn with 10 balls in it. 8 of them are black and 2 are red. We randomly draw out one ball, note its color, replace it, very important, and then draw a second ball, then note its color, put it back, a third, and a fourth. And we want to count, let x be the number of black balls. Let's make a tree diagram, a formula, a table, and graph of the PDF for this distribution. What kind of distribution is it? Go ahead and make out all these things now. Well, let's think about it. Every time we draw this out, since we're putting them back, since it's done with replacement, then this turns out to be a binomial distribution because each one of those draws is independent. we get the probability of 8/10 or 0.8 every single time that we draw a ball out. So the probability is the same every time. This is exactly what we want, and success is drawing a black ball. So this is exactly a binomial distribution. So the probability of success is 0.8, the probability of failure is Q is 0.2, N is 4 because we're drawing 4 balls, and X is a number of balls that we're drawing, the number of black balls that we're drawing, and so that is a binomial random variable. This is a binomial distribution. Here's our tree. Very similar to the tree we had before, since not only is it binomial, N is still 4, so it's the same depth. The only difference in this tree and the one we looked at earlier with the dice is the probabilities are weighted differently. This time the probability of success is 0.8, high success rate, and the probability of failure is 0.2. And so we get a little bit different numbers. The same values here in terms of 0, probably x is 0 is q squared, and probably of x is 1 is p times q cubed, and so forth. Those are the same, but the actual numbers are different because the actual values of p and q are different. And we can get these numbers. One way we can get them, and you see the whole thing here, is with our calculator. First press second and the VARS key to get distribution, and up arrow to get to Binomial PDF, or if you remember where it was, just alpha A, and that gives you Binomial PDF, open parentheses, put in N, which is 4, comma, P, close parentheses. We're not going to put in a K this time or an X. We're going to store it in L1. I can do all that at once. And right here gives us our probabilities. And if we go second, if we go stat, we get this screen right here in the upper right. Hit enter because you're going to do edit, or just press 1. And we get this screen here which has our list 1. And notice this is our probabilities of x equals 0, 1, 2, 3, and 4. So there's the entire table. And in fact, these would normally be rounded off, but in fact, it turns out that all of these turn out to be terminating after 4 decimal places. So this is the exact value of the PDF right there in that table. There's the whole thing right there. Here are the details worked out, and same thing again. And then there's the graph.